If everything is working, you all should be able to see a screen that says preventing bugs with better types. Yes, no, maybe.
Yeah, yes.
Hooray! Awesome. Due to the camera angle, I cannot see anyone in the room unless they are standing. So, verbal will have to be at a bit. But good evening, everyone. As Lee has introduced, my name is Cameron Presley, and if you're in the right room, you're tired of writing code that has bugs in it, and you're intrigued or interested on better ways of doing that. So for the next 30, 40 minutes, depending on how questions go, I'm going to show you some tips and techniques. Lee has already done a great introduction about myself, but software developer based out of Charlotte, North Carolina, MVP in developer technologies. All that means is that I just do a lot of stuff for the community for no pay. Like I don't get compensated for being a speaker, any of that such. I can assure you I'm not getting paid to speak here. It's just when I started out as an engineer, like all of us did, I was kind of smart, but not very wise on what to do. And the community is what helped me out, right? Reading through blog posts, books, articles, Pluralsight, all that stuff helped out. And I got to the point in my career where I wanted to give back, right? I took a lot out and I wanted to put some stuff back in. So starting in 2015, I started speaking at conferences, user groups, things like that. So we're actually approaching almost 10 years. And through some of that, Microsoft's like, hey, Cameron does pretty cool stuff. We think he's pretty cool. Something that Lee did not know, did not tell you about, is I also do woodworking. I'm really bad at it. The only thing I can tell you is that it stands and it works. And the reason why I love showing people this picture is when you learn new things, you're going to struggle. You're going to suck at it, to be honest. And that's okay. Be comfortable with that. That means you're learning. That means you're growing. That means you're going outside your comfort zone. That being said, though, I tried to get Lee's attention, but I think he had a little bit of gin and went through. But I am also looking for a job. So if you get through this talk and you're like, man, Cameron seems pretty smart, I kind of want to work with him, chat me up. See if we can't make something happen. But enough about my shameless self-promotion. Let's get into it. Everything you're going to see tonight is already live. If you trust me, you can scan the QR code. If you don't trust me, you can go to blog.softwarementor.com/presentations. It'll be right near the bottom, but that'll be the link to the slide deck for everything that you see this evening. So momentary pause while everyone grabs their phones and takes some pictures of a blurry QR code. But I've seen some thumbs up. Some will assume that's work. Let's get into it. So first and foremost, when we say type-driven development, what in the world are we talking about? And here's kind of the like my textbook definition, but I want to give some concrete examples too. How many times have you worked in a code base and a bug was found and it's because of a developer did something dumb that they shouldn't have been able to do to begin with, right? Usually because it broke a business rule or something. I know I've worked in code bases like that. Anything that's been stringly typed is fun. We'll say it that. So the idea behind type driven is, hey, let's use our types and define them in such a way to make developers have to work really hard to break the system. And by break the system, I mean like the code won't compile. And if this seems like a crazy idea, well, I'm not the only one to come up with this. Jeff Atwood has a terrific blog post about this called Falling into the Pit of Success. And one of the excerpts I want to talk about is he argues that a well-designed system makes it easy to do the right things and annoying but not impossible to do the wrong things. This blog post has to be every bit of 10 years old, right? It's been around the block a little bit, but the advice still holds true today. And if you don't know who Jeff Atwood is, he was kind of behind this thing called Stack Overflow. So if you've ever used that site or service, you can kind of, thank him for that. Another way to kind of really think about this, though, is you're really making illegal states unrepresentable. Make it such that your code literally can't even do it because it wouldn't compile, it wouldn't run, it wouldn't do whatever. So let's take a look at some examples. Let's say that I have this really cool static function called print color. You give me some string and of color, and I'm just going to write to the screen. This is code any of us could write in C# all day, no problem. And if I call it right, no problems. I can print color for orange, blue, platypus. This will all work. But I don't know about you, but what color is a platypus? Right? Blue and orange makes sense, but I don't know what color platypus is. Right? Here's kind of already an example where our types have been defined in such a way that it allows us to do bad stuff. So how can we fix this? And that's a question for the audience, right? Um, we only want to support a set number of options. What are some types built in the C# that allow us to do that? Enum, that's right, Lee. Oh, it's almost like you looked ahead. But yeah, so one way we can fix this problem is we can define an enum called color. And instead of using a string to represent the color now, we're now using this enum, and this is awesome because we can now have better type checking. So when we try to do print color with those strings, we get an angry compilation error that says, hey, wait a minute, we can't convert from string to colors. You should feel bad, write better code. There's actually a name for this code smell. Primitive obsession. It's when you use primitive types to try to model domain concepts in your code base. I kind of joked a little bit about this before when I said stringly type systems, but that's kind of a good example here. So instead of passing in strings, we pass in the enums and everything is hunky-dory. We know what we can do. But there's some other things that we could have some not great code as well. Let's take a look at these functions. So we've got some more stack methods, and what they're doing is that they're doing some unit conversion, right? The first one's converting kilometers to miles, and the other one is converting miles to kilometers, right? That way we can handle both imperial and metric units the same. And there's nothing wrong with this so far. And then we write some code where we can say, here's 5K in miles, we call a function, we write it to the screen, and we say 10 miles in kilometers, we write some code right to the screen. And we run this. Wait a minute. Wait just a minute. I can go ahead and tell you 10 miles is not 6 kilometers. As somebody who does a decent amount of running, 10 miles would be closer to like 15K. And the problem here is that we used the wrong function. That convert kilometers to miles, we used the wrong one. It should have been convert miles to kilometers. We flipped it. Flipping numbers or measurements around like this is super, super common. In fact, for those of you who've done your research in like safety engineering and such, you know that we've had some like space disasters related to accidentally flipping units around and our code not catching it. And really the problem is the fact that the convert kilometers to miles and it's opposite. They just work on numbers. They have no idea of units. So we got to add that to the typing. We got to add that to the domain. So one way we could fix this is that we could use an enum from before, right? And this time it's only kilometers and miles. And we're going to use a record from C#. You could have also used a class. You could have also used a struct. Don't come after me, right? Just using some stuff here. That now keeps track of a length and what unit that length was in. And the minute we do that, we can create a new function called convert_to that says, if you give me a measurement and whatever unit you want to go to, I'll give you the right measurement for it. And we do some if checking here, and that's all well and good. I don't necessarily care that you're reading all the code. Just realize that we're now working with measurements here and not necessarily just raw numbers. And once we do that now, our code becomes a little bit clearer what we're trying to do, and it's a lot harder to cross-thread something. Now, I'm not saying that this is perfect, but this is loads better than what we had before. And now that we get that 10 miles is like 16 kilometers and all that fun such. So these are some, kind of made up examples I've got for what happens when you don't have a great type system and some of the issues you can run into. Making sense so far? Seeing some head nodding and other such, so I'll take that as a yep. So let's go into a little bit more meat and potatoes of this evening's presentation, which is we're going to be modeling out a subpart of the Blackjack game. Now, I chose Blackjack because it has just enough problem domain to be worth discussing, but not so much problem domain that we're going to be here for a day hashing through it. So I'm going to show you how to identify some domain models, when to use certain typings versus not, and some ways we can handle interesting scenarios like when we don't have data to work with. Now, throughout this part of the presentation, it's going to be mostly F#. It is perfectly okay if you've never used F# before. Not a problem. We'll go over the syntax if and when it comes up. But I should have asked this question to begin with and ask it now. Show of hands or just shout into the speaker. Does anyone in the room have TypeScript experience?
Yeah.
Okay, cool. TypeScript and F sharp, for whatever reason, share a lot of the same syntax. So you may feel almost right at home with this. But if not, just shout into the speaker. I'll pause. We'll hash out whatever the syntax issue is, okay? So the thing with Blackjack is that it's played with a standard deck of cards. And when we think about a card has two things about it, right? It has a rank and it has a suit. So we're going to go ahead and start modeling just based off of this. And we can make some decent progress. So for those of you who come from a more OO background, you may have heard the trick of figuring out your objects by, or your classes by looking this thing for nouns, right? And stop me if you heard this before, but essentially the idea was nouns were your objects and verbs were the methods for them. That approach actually kind of works with functional too. The only difference is that we're not going to attach our functions to the types. We're going to make them independent of each other. So if we're going to be looking at the problem description with nouns, well, let's go back and figure out the nouns. So people in the room, shout it out. What are some nouns that you see in here? That you didn't realize you were getting an English quiz in your .NET talk this evening. We've got card, we've got deck. Yeah, deck cards. We've also got rank, and we've got a suit. Okay. So this is enough for us to get started breaking down some things. So let's do that. So what we've done is I've drawn some circles, one to represent each of our domain concepts. And some of these things are going to be related to other things. So what I'd like to do is then draw arrows between the things that are related to each other. So for example, deck is 0 or more cards, and a card has to have a rank and a suit. Well, the cool thing is if this is our dependency model or our dependency tree, we actually know how to implement this. All we got to do is flip it upside down, and that's our implementation order. And that sounds a bit odd, but I'll give you a reason why. In F sharp, it runs code top down. So it doesn't really jump up and down all over files. Like that's not something you'll typically see. You can open up any F sharp file and read it top to bottom, and you'll know roughly what it's doing. That is something that is more unique to F sharp though in that regard. So let's go ahead and start tackling these different models. And as we're tackling them, you'll see some cool ways we can, well, define them in such a way that we don't break stuff. So let's take a look at rank. So a rank can only be one of a set number of values, right? This is your ace, your 2, your 3, all the way up to the king. So you might be thinking, hey, let's use an enum, right? Enums are great for modeling something of a finite number of choices, right? Well, that works, no problem. And this is valid C# code. It'll compile all that fun stuff. So here's what that would look like in code, right? We can say, well, here's a valid rank. Here's an ace. But then I can do some bad stuff like this, where I can typecast the number 1000 to be a rank. But which one's that one? Is that a king? Is that a queen? Is it a 7? I don't know. And worse enough, the compiler doesn't know either, because you just typecasted that integer to a rank. And that's a problem because enums under the hood are what? Yeah, they're numbers. There's integers, right? So the compiler doesn't have so when this code gets compiled, it actually strips out the enum information and just switches it with integers. So when you're typecasting with rank here, all you're doing is making the type checker happy. It's not actually giving you much of a guarantee here. Well, that's a problem because that means we wouldn't catch issues like this until runtime. And I don't know about you, but if my code's broken, I'd rather figure it out at compile time, right? So that the CI pipeline smacks me on the wrist, not my user calling in support going, hey, I think I just won $1 million at your blackjack table, right? That would be a problem. So here's a way we can solve this problem using what's called algebraic data types. Don't worry about that concept. All you need to know is something called a sum type. If you are modeling a type where it can only be one of a specific value, use a sum type. Here's what that would look like. So this is F sharp code. So the way to read this is that we've got a type called rank, and it can equal ace or 2 or 3 or 4, or all the way down to king. So that vertical pipe is how you know you're dealing with a sum type, and you can read that as OR. Do not get this confused for bitwise OR. It has nothing to do with bitwise. We're not dealing anything with numbers here, right? So don't worry about that. And how our F sharp code would look like this is kind of like the following. So we can define a variable called ace. It's of type rank, and we can set it to the value of ace. That's valid F sharp code that would compile no problem. And if I try to create that invalid rank again, where I try to typecast 1,000, this won't work for all sorts of reasons. Some types aren't numbers under the hood. For those of you who really want to know what the nitty gritty, every one of those cases of a sum type is actually its own class. It's its own actual type. You can kind of think of rank being a base class, and then ace through king are classes that inherit from it. But please don't think about it that way, because that's going to lead you down some real problems. Just think about like, hey, these aren't numbers. Okay. So this won't compile at all. In fact, you'll get told like, hey, yeah, here's what rank can be. It can't be anything else. And so the F sharp compiler is helping us out with that, which is kind of nice. So I call out this GitHub issue. So type unions and sum types do not exist in C# today in any shape, form, or fashion. They're not there. However, there is a proposal on GitHub for C# type unions that's gotten a lot of traction and is currently under progress. There are design meetings. There's even rough proof of concepts happening. So this is coming to the language. I would highly encourage you to check out the proposal on GitHub and see some cool stuff that you can do with it. So the other thing I will kind of hint to you as well is we have type unions and sum types in F sharp. Other languages already have this concept. In fact, TypeScript, language we were talking about earlier, already has something called union types. They're already there. They're built into the language. And you're seeing other languages either having this in by default, or they're starting to implement themselves. So this seems to be coming to be a really helpful pattern. And you might see why a little bit later in this presentation. Enough about type unions, though. We've implemented rank. Let's go ahead and implement suit. So a suit can only be one of 4 values. It can either be hearts, clubs, spades, or diamonds. It can't be anything else. So given what you've seen so far, how would you model this? Yeah, some type. I'm glad no one said enum, because then I'd had rewind 5 slides and we'd do the same talk again. But yeah, we would just use a sum type. So we can say type suit equals hearts or clubs or spades or diamonds. And with that definition, you can't give us bad suits. It won't work. It won't compile. So now that we have rank in suit, we can define card. Now, card is a little bit interesting because it has to represent every combination of rank and suit. So technically, you could have a sum type of 52 options, right? 4 suits times 13 ranks, but I'm lazy. I don't want to write 52 cases. That seems painful. Is there a better way of doing this? So ignore F sharp for a minute, and let me ask you the question in your C sharp. What code would you write if you had to represent some concept that had a rank and a suit?
Yeah, so the values or class.
Yeah, exactly. So maybe your newer engineers are going to do something like this, right? Where they have a public class called card. It's got a rank and suit property with get sets. Engineers that have been around the block may want to try and make it immutable and just set getters. For those with the newer, fancier versions of C sharp, you may just use the straight up record type out of the box. And these are all great ways of solving this problem. Well, guess what? If you're already familiar with this, and especially that last option, you actually know another algebraic data type called the product type. And this is great when you're modeling a type where it has to be the combination of other types. You can kind of think about it as multiplicative, right? That's where it gets its name product type from. So here's the type for card in F sharp. We say type card equals rank of rank, suit of suit. From a naming convention perspective, they typically follow like TypeScript where they do camel casing and not Pascal casing like C sharp. But with this type, if we tried to define a card like ace of spades, here's what that would look like. Let ace of spades it's got a property of rank equal ace, suit of spades. And if you're already coming from a C sharp background, right, this syntax is already kind of looking familiar. It's almost like you just knew up the record in place, right? You also get some better type safety because if I try to create an invalid card, let's say a king of hearts, and I'm trying to set some property called 10 that doesn't exist, the compiler helpfully tells me, hey, buddy, this record has nothing called point. Can't do it. Go back to square one. So that's card. And now that we have card, we can define a deck. Now, a deck represents 0 or more cards. So once again, going back to my favorite C sharpers in the room here, let's say that you have to represent some collection, something that had 0 or more items in it. What would you use? Probably use a list, right? List, IEnumerable, something like that, right? This code should look somewhat familiar. Well, we have that too in F sharp. It's actually called a list. It's closer to a linked list, which actually works out well for us, but that's neither here nor there. The cool thing that you can do in F sharp is you can do something called type aliases. And this is great for when you're saying that a type can be also referred to another way. So for this example, we can say that deck and card list are interchangeable. Anything that works on a deck will work on a card list and vice versa, which is pretty neat. So here's us creating a deck with 2 cards in it, an ace of spades and a king of hearts. Works just fine. And here's us using that deck to do some functionally type things. So a good way to read this is that we're taking that deck and we're converting each of the cards in that deck to only get its rank, and then we're going to print each rank to the screen. I understand y'all are not F sharp developers, so the equivalent C sharp code using LINQ is the following, where we new up a list of cards, we do a dot select, followed by a to list, followed by a for each.
Hey, Cameron,
Hey, what's up?
can you do a global using deck equals list of card or something like that? Isn't there a way to do it global aliases in C sharp with some global uses?
I don't know. I don't know about global aliases in F sharp. That's not something I've ever explored because typically what would happen is you would define, like, let's say you define a deck in this file, then you would open this file. It's literally called open. And then that's what you open that file up into another one. So it'd be kind of like a using statement. But yeah, I'm not 100% sure on that one, Lee. Any other questions? Okay. So at this point, we have defined rank, suit, card, and deck. Now let's get into some of the fun business rules about Blackjack. Getting points for a hand. Right. So at some point in the game of Blackjack, you're going to end up with 2 or more cards in your hand, and we got to figure out how many points you got, right? Because if you have more than 21 points, you've busted. If you have less than 21 points, then you've most likely stayed. And if you've gotten like an ace and a 10 of some sort, you've got a blackjack. But we got to figure out how to sum of these things up. So let's talk about the business rules for points. So every card is worth so many points, and it's based on that card's rank. Suit doesn't matter. If you have a card that's 2 through 10, it's worth that many points. It's worth its rank. So 4s are worth 4 points, 8s are worth 8 points, so on and so forth. Jack, queens, and kings are worth 10 points. So far, so good. Aces, though, are a little bit interesting because they're worth 1 or 11 points depending on what's more advantageous for you. And so, long story short, they're worth 1 or 11, and it depends. And as a developer, it depends is kind of scary because it's hard to code an algorithm that says sometimes I work, sometimes I don't, sometimes I'm this, sometimes I'm not. So let's try to model points as a concept, right? So Points has to fit one of two shapes, right? Because it's either going to be worth one value, right? Or it's going to be worth a set of two values. So should we use a sum type or a product type to try to model this? Yeah, we can. It's actually a trick question because you'll need a little bit of both. But sum type is a great one. So here's what we can do. And this to me is where sum types start getting a lot more interesting. So at this point, you have seen what I like to call the enum style of sum types, right? Where it just had a label, right? Ace, 2, 3, bump, 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 bump. But sum types actually have constructors. And so when we declare like points and we give it two constructors, one constructor is called hard. And if you're going to construct that value, you need to pass me an integer. Otherwise, I'm not happy. I won't compile. If you don't want the hard version, that means you have to use soft. And if you're using the soft constructor, you have to pass me in a tuple of two integers. Now, if you're wondering why I use the words hard and soft, I can assure you they're not keywords or reserved. It's actually the technical term for these points in Blackjack. For example, if you have an ace and a 7, that's known as a soft 18 because you could always draw a card and not bust. Versus a king and an 8 would be a hard 18 because you could bust. So we have points defined as such. So now let's go ahead and write the function. So I'm going to define a function called card to points that takes in, it takes in a card and it's going to return points. So the way to read F# is let the next symbol is the name of whatever we're creating. So in this case, card to points. And then if we have some other names coming in, F# knows that this is a function and it's actually going to start deriving types based on how you use stuff. Now, at this point, if you're writing this in a file, it wouldn't know that you have a card right now, but you'll see why in a second. So it's going to take in some letter C, and it'll be a type card, and it's going to return us back some points. If you have a TypeScript background, then this syntax is going to look very super similar to what you're used to. But once we've defined all this, we're going to do that equal sign, and we're going to do some pattern matching. And I'm going to say match on the card's rank. And the minute I write match c.rank, F# immediately knows, oh, this has to be a card. Because I've not seen any other types with a property on it called rank. Has to be a card. So one thing that will throw engineers off when they come to F# is the little typing you have to do to make things work. F#'s type system is so strong that it can actually just figure it out most of the time. For those of you who like to do a lot of reading, the technical phrase for this type system is called Henley-Milner. Quite a few other languages use this. Haskell is one that comes to mind. But if that's something, Friday evening, looking for something to do, just need a good blog post to read up on, would recommend it. But we're going to match on rank. And the minute we match on rank, F# will auto-generate some all the cases for us. So the first one it's going to generate is ace. And we go, all right, cool. If it's an ace, arrow over, okay, that's worth 1 or 11. So that's a soft value. Kind of like what we talked about in our business rules, right? Our 2 through 10 are going to look like the following. We're going to say, okay, if it's a 2, return back a hard of 2. 3, hard of 3, bump, 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 all the way down to hard of 10. And then once we've got those defined, we can do the same thing for Jack, Queen, and King. Say those are all hard values of 10. So we've got a function that has matched on all possible ranks. So there's no way we're going to get like a, hey, I don't know how to process this issue. And it knows how to give us points. So that's pretty cool. One thing I did not show here is that let's say that I forgot to put some cases in for Jack, Queen, King. F# would have nagged at me and it would said, hey, yeah, you don't have all your cases covered with rank. And it would have given me specific examples of which one I didn't cover, which is really nice when your pattern matching gets a little bit more complicated. The fact that it can give you cases that you've missed. So that's kind of convenient. So we now have a way to go from card to points, but now we got to have a way to add them up, right? And the problem is we can't just use regular addition because we don't know how to add two hard values together, right? Or how to add a hard and soft value. So we got to figure out what those rules are, and I'll help you out. So if we have two cards, or if we have two sets of points that are both hard, we just add their specific values together. So if we've got like a king and a 7, that's a hard 10 and a hard 7, we should end up with a hard 17. If one of the cards is hard and the other one is soft, then we're going to get back a soft value, and it's going to be the sum of hard with both values of soft. So if we have an ace and a 7, that's a 1 comma 11 being added to a 7. That should give you an 8, 18, because we're going to add the 7 to the 1 and to the 11 separate. And then in the case that we have two soft points, then we're actually just going to take the low of one of them and add it to the other. So in the case you have two aces, if you did all possible of adding, you would get like 2, 12, 12, and 22. 22 is never a valid score, so you chuck that one away. So you'd end up with 2, 12, and 12. You don't need the other 12, so it's just 2 and 12. Sounds really complicated, but once you start writing this out, you'll see it's not too bad. The bigger thing to note, though, is that we've got some rules. Making sense so far? Thumbs up, yes, no, maybe. All right, cool. I've got some degenerate gamblers in the room then. Excellent. So let's write a new function. Let's write a function called add points, and it's going to take in two parameters, A and B. And you might be thinking, Cameron, your input names suck. These are terrible parameter names. Well, here's why. A trick I like to follow is your variable names should only be as long and as meaningful as their usefulness. You'll see that A and B are kind of pointless to us for what we're doing. So I just call them A and B because they don't really have a ton of value to me besides that. So we've got a function that's going to take in two sets of points and it's going to return some more points. And we're going to do pattern matching. And this is where we start really doing some fun pattern matching here. Because the minute I say match A and B, F# knows that I'm going to have at least 4 cases to make this work. So the first case is if they're both hard. And if they're both hard, I'm going to give their integers that they're wrapping names. The first one's going to be called X, the other one's going to be called Y. And this works because if you recall, if you have a hard value of points, it has an integer, right? That's its constructor. So if we've got two hard values, we return hard of X plus Y. Not too bad. The other scenario is if the first card is hard and the second card is soft. And if that's the case, we're going to do exactly what our business rules say. Go, all right, cool. Well, we're going to return back a soft, and we're just going to take that hard value and add them to the tuple of soft. Now, we're pretty lucky that addition in this way is commutative. That means it works either way. A plus B is the same thing as B plus A. So if the first card is hard and the second one is soft, it's the same thing as saying that the first card is soft and the second card is hard. We'll get the same results. And then our last case is if they're both soft, so X, Y, and you'll see me use that underscore character. That's a discard. That means, I don't want it. Get rid of it. I don't care about it. And we're doing the addition this way. And once again, if I hadn't handled one of these cases, F# pattern matching would have absolutely nagged at me and said, hey, Cameron, you didn't do this right. Do better. Which is kind of convenient. So I'm going to take a pause here and I'm going to pick on Lee a little bit. Lee, how are we doing in the room? Is this making sense? Are there questions? Because I'm going to be honest, if y'all are already picking this up on F#, man, y'all are a lot smarter than I am. Because this took me a lot longer to pick up.
You're doing an excellent job communicating. You have an attentive room, so you're nailing it, Cameron.
All right, thanks, Lee. So we have a way to go from card to points, and we have a way to add points. So now we can actually score a hand. Oh, but wait. Business rules. So we're adding points together, right? So we're going to have to figure out some way of what I like to call normalization. So let's say that you have an ace, a 9, and a king. Well, if we have that, I'm sorry, Lee, was that something in the room?
I'm sorry.
No worries. So if we have an ace, nine, and a king, that's worth a soft of 20, 30, right? Because if we treat the ace as a 1, you've got 1 plus 9, which is 10. 10 plus the king is another 10, so that's 20. If we treat the ace as an 11, though, you have 11 plus 9, which is 20, plus the 10 of the king is 30. Here's the problem, though. 30 is a bad score, right? If you've gotten 30 at a blackjack table, the dealer loves you, man, because you just gave him some money, right? So you don't actually have a soft 20-30. You actually just have a hard 20, because if you were to take on any more cards, you would bust, right? You have a very high odds of busting. So let's write a function to help us out with this, because of course we are. So we're going to write another function called normalize, and it's going to take in p for points. And then we're going to match p with one of two things. If it's a soft value, we're going to use something called a guard, and that's that win part. So the way to read this line is say, match p with soft xy, but only if y is greater than 21. If that's true, it's going to go into this case. And yeah, if it's more than 21, then you're no longer a soft value. You're going to get x. That's all you can work with. Otherwise, don't care. You can kind of think about this as a default. Just return back points because there's no work to do. The cool thing is, and I wrote this code specifically, there's no types here. Notice how I didn't have to explicitly say what P was. And I don't have to explicitly say what type normalize returns. That's because F# figured all that out. Like the type system's already figured out, like, oh yeah, this is points coming in, points going out. I've got you. Kind of powerful. But we've got this normalize function. So now let's update our add points function to use it. So I've actually wrote a function inside add points for normalize. That's where I shoved that logic at. And then I've got this let points equals the addition logic that we had before. And then so what we're going to return is normalize invoked with points. So that's our yeah. What you got, buddy?
Yeah, so I got a dumb question. Why don't you have to worry about x being greater than 21 and returning y?
Yeah, that's a great question. So the reason why I don't have to worry about that, Lee, is because the way I define that tuple, the first value is always the lowest one. And if the x one's also greater than 21, then the score is going to get caught when we convert the points to what I call a score. So let's go with your example there, Lee. Let's say I had a soft, make sure I pick up an example that works. Oh yeah. Let's say that I had something that was like, oh yeah, here's a dumb one. Let's say that actually had a soft 11 and 21 and someone draws like another, actually that still wouldn't work. I don't care about X because if both of them are greater than 21, it'll get caught when I figure out someone's score of whether they busted or not. I only care about if the Y is greater than 21 to force it to hard. Also, because the way I'm doing the math is I'm always enforcing the lower values, the first one, not the second one. Does that help?
Yeah. That's the answer.
Okay. One thing that I'm surprised no one's asked the question about, and I'll say it here, you don't typically see return statements in F# because it's assumed that the last statement in the function is your return. That's why I only like let normalize P that match with. That's an expression. So whatever that returns, that's what you get. That's how the let points equals match, all that works. So we've got a way to go from card to points. We've got a way to add points. Now we need to score a hand. So here's what that would look like. We create a function called points for hand. Let's see if I've got the, oh, nope. We got a function called points for hand. It takes in cards and it's going to return us back points. What we're then going to do is say, hey, cards, we're going to convert each of you to points. And then we're going to use a function called fold. And how fold works is that if you give it a way to add two elements of the list and you give it some initial state, it'll know how to combine everything. For my C# engineers in the room. Oh, I'm sorry. Yeah, it's exactly aggregate. That's why I've got the comment below of essentially what it's doing. Though I do see that I'm missing a semicolon, so technically that code won't, or not a semicolon, a closing parent, but that's okay. But yeah, we're essentially saying, hey, cards select, convert each one using card to points, and then do an aggregate. That's exactly right. Um, if you're coming from TypeScript, you already know what map is. Instead of fold, you would know it as reduce, but it's the same concept. But yeah, we just figured out how to get the points for someone's hand. That's pretty cool. And I haven't really talked a ton about this, so I'm going to talk about it now. How many of y'all in the room have experience with like unit testing? Right? Like you've written some unit tests, maybe even some TDD. I want to back up a little bit. If you had to, so I know this is F sharp, and you've never done testing with F sharp, but think about what the C sharp code equivalent would look like. How hard would it be to write unit test on this? Given this state, make sure it converts it to another state. Probably wouldn't be too bad, right? Because it's almost basic unit testing because there's no mocking, right? There's no integrations or anything like that. Let's back up a little bit more. I'm going to back up a lot here. It's all right. This will be great for the recording. Let's say you had to write test on this function for card to points. That'd be pretty straightforward because you're really just saying like, hey, if I pass on a card with this rank, do I get these points back? What I find with functional programming concepts in general is that I end up writing lots of small functions that are stupid easy to test. And then once I've built all my Lego blocks, sorry, you're going to see me fast forward here a little bit. I then end up just putting them together like points for hand, where I can't really screw up the implementation too terribly bad, right? Because I don't have to test that select works, because if select is busted, then C sharp's busted, and that's a problem. I don't really have to test that aggregate works, because if aggregate doesn't work, that means C sharp is busted. Once again, I've got bigger problems. So it's this ability to write smaller blocks and plug them together. You'll hear an expression called pipelining or chaining. That vertical bar and that greater than sign is exactly that. Take the thing on the left, shove it onto the right. So take cards, map it, then fold it. You'll see that a lot in code. All right. You're all doing great. Stick with me for the next little bit where we talk about drawing a card. So at some point, we're going to need to draw a card right from the deck because someone's going to want to hit. It's going to happen. Or at some point, someone's going to have a hand. So we're going to write a function called draw that takes in that deck of card list, and it's going to return back the card that was drawn and then the rest of the deck. So we're going to pattern match on that deck with the following. Open square bracket, closing square bracket. That means if the list is empty. So, and this is really common when you're working with lists, is that you typically pattern match on an empty list. And then I want you to pattern match on, okay, this is a list. Here's the first element called head. Here's the rest of the list called tail. So if I've got a head and tail elements, cool, that's your tuple, right? First element's the card that you drew. The second one is the second element is the rest of the deck. But question for the group. What happens if my deck is empty and I need to draw? What should happen? Yep. So yeah, all sorts of things could be happening here. So in this case, I'm throwing an exception, but I think we can all agree throwing an exception here is less than ideal, right? So, but let's say that we keep this code here, and whoever said null, hold on to that. I want you to hold on to that really hard because we're going to talk about that in a second. But let's say this is our draw code. And now we want to write a function called draw multiple. So you give us a deck and we'll give you back a list of cards that were drawn and such. So we're going to draw that first card, and then here's our new deck. We're then going to draw a second card, and then we're going to return you back. Here's your card, second card. So here's the cards that you drew, and then here's the remaining deck. Here's the problem, though. This this code will compile, but when I try to run this with an empty deck, it's going to chuck an exception. Remember that thing we talked about way at the beginning about I want developers to do the right thing by default and not bad things? The type system doesn't help me out here because it doesn't warn me that's about to throw an exception. This is also one of my big complaints with C#. Unless you happen to know the methods you are using, i.e. you memorize them, you don't know if a method can chuck an exception. There's no clue, right? Unless it just happens to be in the docs. This is one of the few things I think Java actually does pretty well. Is there anybody in the room who has a Java background or has ever worked with Java? All right, cool. For the gentleman nodding his head, checked exceptions. I bet this is ringing a bell for you. So if you don't know what checked exceptions are, it's this thing that if you write code in Java and it throws an exception, the Java compiler will force you to handle it. If you ever call that method. Like, so in this case, since draw throws an exception, if I was in Java and I called draw, but I didn't wrap it in a try catch, the code won't compile. Java will nag at you until you fix it. On one hand, that's really cool because it's forcing me to fix it. On the other hand, most engineers just write an empty try catch around it, swallow the exception, and guess what? No one did the right thing anyway. So boo for everyone involved. Let's talk about a better way of handling this problem, shall we? So at the end of the day, this is a really common pattern that happens in any code base. Yeah, you told me to do something or to go get a value and I can't. It's not in the database. I don't have that file. I don't have it. Like, I can't do the operation. So ways we deal with this, right? You saw one with exceptions. Someone mentioned null, right? Null used to be a lot worse in C#, but when they started adding the nullable reference type checking, that has helped out a ton. However, not all of us get to work in nice clean code bases like that. So null has its own set of problems. And if you're a big fan of design patterns, you may have heard of the null object pattern where it says, okay, if I can't do it, you're going to get back like an empty object that's safe to work with. But that opens up its own can of worms too. So exceptions aren't great because your code could blow up without you ever realizing it. Not cool. Null isn't always great because either you have to wrap null logic checking everywhere, or if you're lucky, you can opt into the nullable reference type such, which will help you out quite a bit, but still not perfect. You could also do the null object pattern, but then you've got to figure out like what's an empty default. So think like if you're drawing a card, what would be an empty default there? Right? If the deck's empty, I can't give you an empty card. It doesn't make sense. Right? A joker? Okay, now I've got a code for joker everywhere else in the code base, right? Like I'm stacking problems to solve other problems. Thankfully, we have a solution to this. So in F#, it's called option, and it's a sum type. An option, so if you're wondering what like the single tick T means, that's a generic. It's just a generic value. So option has one of two constructors. You either construct the sum version of it, and that means you have to give me a value, or you construct the none option, the none constructor, which you don't give me any values. This is called option in F# and in .NET. Almost every other language calls this maybe. So if you're like, I'll throw a dart in the room. Anybody like big fans of Rust? Ever worked with Rust? Cool. Rust has option types built in. Same concept. I'll go and tell you this. F# has options built in as well. This is free out of the box in the language. So for the gentleman who's nodding his head, raising his hand, like you already know where we're going. But once we have option, let's go update some of our functions now. So let's get rid of draw and let's use safe draw. So how safe draw works is we're still going to match with the deck, and we're still going to do the pattern matching on if the deck's empty versus if it's got an element. But the differences are, though, is that if the deck is empty, we're going to return back none. There's nothing for us to do, right? We couldn't do the job for you. Otherwise, if we do have something, we're going to return you back some head element, which is the card, and then the tail, which is the rest of the deck. And you'll also tell in the light gray that my type signature has changed. Before, this said card and card list. Now it says card and card list option. That option provides a lot of protection for us, and I'll show you what I mean in a moment. So let's say that we're going to draw multiple cards again, right? Like we did before. Well, so we're going to call it safe draw multiple. We're still going to take in the deck. We're going to match that safe draw. And now we actually have to match with it because it's coming back as an option. So if it's none, okay, cool. If I couldn't draw any cards, I can't continue working, so I'm going to bail out with none. I'm going to short circuit. Otherwise, I was able to draw a card, and here's what I got back from drawing that first draw result. Here's the card I drew, and then here's the new deck to work with. So if this works, I'm going to draw again, except now I'm drawing with that new deck, right? The deck that's already got one card taken out of. So I'm going to pattern match again. I'm going to get none. So if this fails, you get none. So in this case, is like, yeah, I was able to draw one card, but I couldn't draw two cards. Sorry. Here's you get nothing back. Otherwise, it did work. Here's exactly the second card we drew, and then here's the deck that we got back. And now we can say, all right, cool. Since this worked, you got back some, here's your card, second card, and then here's your new deck. This works. Ugh. There's a lot of, like, if you're thinking about this like if statements, there's a lot of nested ifs going on, isn't there? That's not cool. So now I'm going to show you some really awful code here. So option is built into F sharp, like I was alluding to before, and they've got some helper functions you can use called bind and map and all that. You can look at this code. This still sucks, right? This is pretty hard to read. And if someone put this in a PR, I'd be having some like, hey, I'm going to teach you something new today type conversations. So I'm going to teach you something new. One of the coolest things about F sharp, and this is something unique to F sharp, is that they have something called expression builders, specifically called computational expressions. There's your $10 word of the day. Now, a computational expression is I'm not going to go too deep in details, but just think about it like this. We can define something that automatically can do map and bind and return for us. And the minute we do that, we can then simplify a lot of that pattern matching, right? Because in our first version of draw multiple, that was really nice, right? We just said, let draw, here's your results. With option builder, we can do that again. The only difference though, is that we've put it inside that computational expression of option. And now you're seeing some let bang happening. Let bang says, hey, this may or may not work. So when we say let card new deck, safe draw of deck, when we say let bang, that's telling that's actually getting to the bind operator here where it says like, hey, if I work, cool, call the next function. But if I didn't work, short circuit with none. So try to safe draw, try to draw a second time, and if both of that works, great, here's your results. This code looks almost exactly like our original draw, except now this is actually type safe, and we've got the compiler making sure that we're not going to do something dumb. Kind of convenient. So with that, we're going to wrap up here. Y'all, we covered a lot tonight. A lot more than I thought we are going to cover in the last 50 minutes or so. So the three things, though, is what do we learn? First, hopefully you learned how to use nouns to identify your model types, right? That's how we were able to get like rank and suit and card and deck and figure out the relationships between them. We also talked quite a bit about sum and product types and how you use one over the other and why you would use one over the other. We also built out some really cool stuff, right, with functions and mappings and all that. And then we spent a little bit of time talking about how do you deal with missing values using option. A lot of stuff covered here tonight, but if all you remembered was like, oh yeah, there's something called like sum types and product types, and if I design these in such a way, I can make sure that my engineers don't do stupid stuff. If that's all you got, that's great. That being said, thank you all so much for letting me speak at caparea.net user group this evening. Once again, here is the QR code for the slides and additional resources. You can always ask me questions. Let's say though that you've got like a more like thorough question. You can always drop me a line at cameron@softwarementor.com. Otherwise, thank you all so much for your time this evening. So if anyone's speaking, it's actually quiet. I couldn't even hear the clap. So like I don't.
We did clap.
It was raucous clapping. Everyone was.
Honestly,
Lee was dancing on the table. He came like off to the side, like got his shirt off, put your shirt back on.
honestly, I just thought it was like a really good golf clap. I'm like, man, Lee was able to get everyone to do like a solid coordinated golf clap. Like that's amazing.
If there's not any questions, then you could probably let them off the hook and stop the recording. Any questions? Going once? Twice? Okay, there's Lee's face.
Lee.
There's probably a way to turn that on. Great.